Lesson 33, matrix simultaneous equation. We'll be able to solve simultaneous equations with matrices. Today's fact is a pretty interesting here. It's like for 33. It's just like what's 1 factorial plus 2 factorial plus 3 factorial. 1 factorial is 1 factorial equals 1. 2 factorial equals 2 times 1. And 3 factorial equals 3 times 2 times 1. So I think it's, if you add these up together, you get 3 times 2 is 6. I don't know. This doesn't work. I think this is not for, I think this is for a different one. I don't know. I don't know what. I don't have any good facts for 33. For some reason, 33 is just a really lame number. Like, it's just like, yeah, cool. You're 11, you know, you're 11 times, you're 11 times whatever, like you're 11 times 3, but it just is kind of a boring number. So if you guys have got an interesting fact about 33, let me know. This fact didn't even work, so I don't even know what the point of it was. Maybe it was like you're supposed to keep going, like 4 factorial, which is, but that's 24, so that wouldn't work either. So I don't know. I'm going to leave it there though, because we've got more important things to do. So today what we're looking at is simultaneous equations. Now, where are we coming from? We're coming from a big idea. We have just come out of, on Thursday, last Thursday's lesson, we talked about how to make the inverse of a matrix. So what is the inverse? Well, the inverse of a matrix was, we started off talking all the way back in, started talking about inverse matrices all the way back in last Wednesday. So last Wednesday's class, we said the inverse of a matrix is like a special matrix that takes you back to the identity. The inverse of 4 is -4 because that takes you back to the identity, which is 0. The inverse of 7 is 1/7, which takes you back to the 1. It's like undoing it. If this is times by 7, it's multiplying by 1/7 and undoes it. If this is add 4, the subtracting 4 undoes that. If this is m multiplied by m, then multiplying by inverse of m will cancel that out. Then what we did was we spent some time talking about how do we actually find the inverse. The first thing we did was we talked about the determinant. The determinant, or det A, is found by taking this and subtracting this and this. So the examples that we did these 2 examples. Let's just do this C1 again. So to do C, so the determinant of C is going to be equal to -1 times -2. So that's this and this, minus the other diagonal, minus this times this, which is going to be 4 times -3. Now, if you do these, you go -1 times -2, that's going to be 2. 4 times -3 is going to be -12. Negative times negative makes positive, plus 12. That's going to be 14. So that was our determinant. Now, once you know the determinant, you can actually do some fancy, funny things. You can actually say, well, we can then do the next step. The next major step is to then say, well, then once you've got these, you jumble these around. The A goes to where D is, and D goes to where A is. And then the A and the B, they become negatives. So that's how this becomes. And the reason we need the determinant is because it goes out front. Now, the last thing I think I showed you guys, I was going to show you guys, let's grab a look at one more example before we do it, because I want to show you a similar example to the one that I gave. I showed, I think it was, maybe it was Nathan at the very end. I showed a quick little example, but I want to show you guys one more example. You guys can jot this one down if you want, but it's up to you guys. I'm just going to do this on this blank page here. Let me know if you can't see what I'm doing, But what we're going to do is I'm going to make up a matrix, and we're going to do a very specific matrix. We're going to do, I'm going to see if I can make positive. Yeah, okay, so we're going to do that. That means that this has to be that. So we're going to go, and then we're going to go with this. Okay, so let's go look at, let's find the inverse of this matrix here. So we're going to call this matrix B. So what we're going to do first is we're going to find the determinant of B. Okay, so can someone tell me either in chat or out loud, what do I need to do to find the determinant of V? What steps do I need to do?
Isn't it like 5 times 4 minus 3 times 10, if I remember?
Close.
Oh wait, is that other way around?
10 times 3 plus minus 5.
God damn.
Yep, you are right. It's the other way around, but Henry, you were very close to the right technique. So we got 4 times 5. All right, here we go. Now let's plug in the numbers. So 10 times 3 is going to be 30. 4 times 5 is going to be 20. 30 take away 20 is going to be 10. Beautiful. Now, to find the inverse of V, we need to have 1 over the determinant of V. And then we also need to, okay, can someone tell me, what do I need to do with the positions? What do I need to swap?
Swap the 3 and the 10.
3 and the 10. So what goes in the top corner?
10.
Beautiful. And that's a 3. What about the other two diagonals? What do I do with those?
You inverse it. Right?
What do you mean by inverse it?
Like -5 and -4.
-5, -4. So they
Yes,
stay
sir.
where they are. That's really important. Now let's go have a look at this. So the depth V, that's going to be, well, here's the determinant of V, it was 1 over 10. So we're going to have 1 over 10, 10, -5, -4, 3. Now you can just leave your answer here like that. That's fine. That's okay. But if you want to, if you can leave it here, that's fine. It's okay. But if you want to then solve for the rest of it, you can actually just multiply 1/10 into all of these. And the reason that I've chosen 1/10 is because that just makes this life a little bit easier. Why? Because -4 is going to become -0.4 if I divide by 10. And 3 is going to become 0.3. And -5 is going to become -0.5. And 10 is going to become 1. So that's why I use 1/10, is because it just means that this whole, well, that's why we got 1. That's why I made this question, because then you get 1/10, which is nice and easy here. So that would be the inverse of V. And how can you check that? Well, you know, stuff it. Let's go all the way, because we've got a double period. We might as well go all the way. Let's do in this top corner here, V times inverse of V. If I bring out my V, which is, and you can do this in any order, 3, 4, 3, 5, 4, 10. And then we've got 1, -0.5, -0.4, 0.3. So then if we want to multiply these two things together, that's going to give us 3 times, we're going to go across this way, I'm going to go down this way. 3 times 1 is going to give us 3, and 5 times 0.4 is going to give us -2. So therefore 3 take away 2 is going to give us 1 in that corner. If you don't believe me, 0.4 times is the same as saying 4 over 10, which is the same as saying -2 over 5. So if you multiply that by 5, it's going to give you -2. If you still don't believe me, buy yourself a calculator. 3 times this column, 3 times 0.5 is going to be -0.5. and 5 times 0.3 is going to be 3 times is same as 3. It's going to be essentially 1.5. So negative 1.5, 1.5 is going to be 0. Let's just do this bottom left-hand corner. 4 times 1 is going to be 4. 10 times 0.4 is going to be 4, negative 4. 4 and negative 4 is going to be 0. And then this last one, pink. 4 times 0.5 is going to be 2, negative 2. And then 10 times 0.3 is going to be 3. Negative 2 plus 3 is going to be 1. Here we go. There's the identity matrix. Everyone is happy. So let's go back over what we did here. The main thing that I wanted to show you guys is this is how you find the determinant. It's this diagonal minus this diagonal. Once you got how do you find the inverse? You take the determinant, you shove it in here. You take these two numbers and you swap their places. And then what do you take with these two numbers here? They both become negatives. So that's why we've got negative 4 and negative 5. And these two have swapped their places. Then because we've got 1/10, we can multiply that out. And because we know these are inverses, if I multiply them, I get back to the identity matrix. Let's see now. Simultaneous equations. Now, we've already talked about multiple ways to solve simultaneous equations. We've already talked about how simultaneous equations can be solved with the graphical method. We've already talked about how simultaneous equations can be solved with the elimination method. We've even done substitution, but believe it or not, you can also use matrices. Matrices can be used to solve simultaneous equations. Now you might say to yourself, okay, why do we need so many tools to solve simultaneous equations? Well, the power of matrices in this approach is that it can solve many equations at once. So whilst so what does that mean? Well, I can actually show you briefly over here if you'd like. In order to solve a linear equation, you need to have at least two equations. With these two equations, you guys can work out that A is 6 and B is 4. That's enough information to be able to solve these two equations. But what if I said A plus B plus C equals 10 and A minus B plus C equals 2? Then you don't have enough information to calculate A, B, and C. So in order to solve this, you would need to have 3 pieces of information. Now you have enough information to solve for A, B, and C. And you can actually still use elimination and substitution methods. You can even use graphical methods, but now your graph has to be a three-dimensional graph or a two-dimensional graph. And that's fine, but it gets a little bit more confusing to do those. And then if I make it even worse, if I go, if I add another term in there, then I need to have another equation. And that will be, and then you've got 4 equations, and it's going to be even harder. The power of matrices is that they can take something like that and destroy it so easily. So that's what I'm trying to say, is that matrices can take all of these equations and just destroy it and solve it super easy. So that's why we use it. The reason we use matrices is because they're really good at solving many equations at once. Now, you might, sorry, just give me a sec. Okay. Now you might look at this question down the bottom and think, how the hell am I going to turn this into a matrix? and I want to show you guys. So we're going to turn these two equations into a matrix. Now, if you look at these, I've actually chosen these for a reason, because these two equations would be difficult, not impossible, but difficult to do with these two methods. If I had to choose, I would go with elimination method. I multiply the top one by 3, the bottom one by 4, and then add them together. That's how I would do it. But I want to show you guys that this can turn into, and I'd like you to copy this down as well, this here, 3, 5, 4, -3. Now, can you guys tell me, where does this, someone either out loud or in chat, where does this 3 come from? Where did I pull this 3 from?
It's the coefficient of x in the first equation.
It is the coefficient of x in the first equation. And what about the other terms?
They're also coefficients of other, like from the first and second equation.
Yeah, so all of these are the coefficients. So this is, whoopsie, so this is the coefficient of 3, this is the coefficient of y, this is the coefficient of x, and this is the coefficient of y. So, what if I did this? What if I multiplied this matrix by this? So let's take a moment just to grab a look and to see what would happen. If I was to multiply this matrix by xy, I would end up with the top, I'd end up with a 2 by 2 matrix. Sorry, I would end up with this is a 2 by 1, 2 by 2, and this is a 2 by 1. So I would end up with a 2 by 1 matrix. And that matrix would be 3 times x plus 4 times y. And it would also be equal to 5 times x minus 3 times y. Can you guys see that by multiplying these two matrices together, I get back to these two sides of the equation?
Yes, sir.
So what I can do is I can actually change this. I can actually say that, I'm going to put this up here just because I don't want to get rid of that. 3, 4, 5, -3. If I take this matrix and I multiply that by x, y, I will get a matrix that looks like this: 10, 7. Because this here equals 10. Why? Because this equals 10. So that's how I can create, that's how I can turn an equation into a matrix. That's our first step. If we want to try and solve simultaneous equations, then we need to know, how do we put these things into a matrix? Now, this is what we've been building up to, guys. This is why, one of the reasons why I could not teach this on Thursday so that I could do a test on Monday, because I was like, I don't think I'll be able to teach this in one day. But yeah, this is a buildup of multiple ideas. It's a build, this is just completely us exploring the idea of matrix multiplication. And now you guys can see why matrix multiplication is set up the way it is. It's set up the way it is so that you can, as long as you set this up correctly, you can have as many terms as you want. We can have x, y, z and have like a third coefficient at the end. Now I'm going to change the slide. Is there any questions on this before I change the slide? Okay, so fine. Okay, so what? cool. So now we have a way to turn equations into matrices. But then why did I spend so much time doing this whole stuff about inverses if like we don't need them? Let me show you. Let's take two equations, right? We're going to take, on the left, we've got a times x equals b. And on the right, we've got 3 x equals 12. Now, the reason we're going to do it like this is because I'm going to assume that this here is matrix A. This here is matrix X, and this here is matrix B. So that's where these terms are coming from. So before we even do anything, let's just have a look and see if we can. The main idea for you guys here is the reasoning why we can do this. And the reason I've got this line here is just because I found when I showed students this line, they were a bit confused. But when I compared it to, when I compared it to stuff that they were comfortable with, it was like, oh, okay, I can see it. So let's just say we wanted to solve this equation and we wanted to find out what x is. Now, I know a lot of you guys can just easily go, oh yeah, if I multiply this by, if I divide both sides by 3, I find out what x is 4. And that would be correct. But I'm going to show you another way you could solve it. Another really pointless and very long way that you could solve this. And you might be saying, sir, why do you want to show me a really long and pointless way? Because it's going to obey all of the rules of matrix multiplication. Let me show you how. We're going to take this 3 and we're going to multiply both sides by 1/3. Okay? That's the equivalent of dividing by 3, but we're going to multiply by 1/3 instead. Now, what would that look like in matrix land? In matrix land, that would look like multiplying both of these by the inverse of A. The inverse of 3 is 1/3. The inverse of multiplying by 3 is multiplying by 1/3. So I multiply both sides by 1/3. That's why I'm multiplying both sides by the inverse of A. Does this make sense? I'm going to let you know what? No, don't even answer that. I'm going to let you guys take a minute just to absorb what the hell just happened there, because otherwise, and if I say if that makes sense, people are going to, yeah, of course, because they don't want to look stupid. But yeah, let's just have a look at, see if you can think about what that means. Also copy down. Now, the reason we've done it is because, okay, so someone's thrown up a question in a private sort of thing. They've said, what is the x? The x is the unknown, just like how the x is the unknown here. Oh, whoops. Just like x is the unknown here, the x in this case would be the x in this case would be the xy. So 3, 4, 5, -3. 3, 4, 5, -3 equals 10, 7. So the idea is that this is the A, this is the X, and this is the B, right? But the idea that I want you to take away from this is that we're just performing the same operations that we would normally do to solve for what X is. The first thing we could do is if we multiply this side by 1/3 and this side by 1/3, then that would be the same as dividing 12 by 3. And to do that, we have to multiply this side by the inverse and this side by that same inverse. See how these thirds match. Now I'm going to take it one step further. Now, it just so happens that if I multiply 12, a third by 12, I'm going to get a number 4. Great. And if I multiply a third times 3, I get 1. Perfect. Why do I care about that? Because on the left, the same thing happens. See how here I say a third times 3 gives us 1. It returns us to the identity. So A times inverse of A times A is going to take us back to the identity. And that's all we've done here. Okay? That's the algebra that we're doing here. Now, it just so happens that when you multiply anything by 1, it stays the same. So our final answer on the right is going to be, well, that's just going to ignore. So we're just going to get x equals 4 is our final answer. And on the left, it's going to be exactly the same thing. When I take the identity matrix and I multiply it by matrix X, it doesn't matter what matrix X is, it's going to be the same. Anything multiplied by the identity will be the same thing. So if I multiply the identity by X, then it will give me out X. And so now I have X on the left and the solution to the unknowns on the right. Just like how I have the solution to the unknowns on the right. Now, normally I would say to you guys, you don't need to, normally I would say to you guys, you don't need to understand this. You can just jump to this bottom line. But I can't say that for this. Part of finding the solution to simultaneous equations is understanding what's going on here, to the point that I will ask, one of the expectations in tests and the exam is if it says to solve a simultaneous equation, then you show me these steps. Now, the reason that you show me these steps is so that when you get to that final step, you're not pulling it out of nowhere. You're not going, oh, look, magically this happens. You need to show me the logic that you go through to get to this. Now, I could very easily ask you guys whether you understand this. And I know that many of you guys would say yes, because the ones that don't understand it are not going to say, I don't understand it. But from knowing you guys, knowing your 11s quite well, I know that many of you guys are like, what the actual hell is going on here? So what we're going to do now is we're going to do a full example of this. This is going to be one of the hardest questions we're ever going to tackle as a team. So you guys being focused on this is going to be really important. There are questions like this in the exam, so therefore I need you guys to make sure you're focused. Okay. Let me show you. Okay, so Dylan, someone said to me, how do we get the inverse? Why do we use the inverse? Let me just try and explain that before I move on. The inverse of a third, the inverse of 3 is a third. Why do we want the inverse? Why do we want the inverse here? Because if we go a third times 3, that's going to give us 1, which is the same as not doing anything at all. It's like by multiplying by a third, we cancel this multiply by 3. Okay? The same happens here. By multiplying by an inverse, we cancel out this A. which leaves us with just the unknowns. And then once you have just the unknowns, you'll be able to solve it. Let's do an example, and it's going to be one of the hardest examples we do, but we're going to try and do this example here. Okay? We're going to try and do this example here. 5x plus 2y equals 21, 7 plus 3y equals 29. These are already some ugly numbers, but it's okay. We should be able to solve these. Okay. So the first thing we're going to do, the first thing we're going to do is we're going to say A equals 5, 2, 7, 3. We're going to say x equals x, y. And then we're going to say b equals 21 on 9. Oopsies. No, we're not. 21, 29. Okay. Now, like before, we know that if we take this matrix here and multiply it by this matrix here, we're going to get 5x plus 2y, 7x plus 3y. 7 times x, 3 times y. 5 times x, 2 times y. And we also know that when you multiply those all, you get 21 and 29. So once we've done this, we can then do this idea here. Ax equals b. This times this equals this. 5 times x plus 2 times y equals 21. Then I can say, if I take the inverse of A and I multiply it by AX, that's going to equal the same as taking the inverse and multiplying it by B. Why am I doing this? Because the inverse of A times A is going to give you the identity. And when you multiply anything by the identity, it stays as the value. So when I multiply identity by x, it just stays as x. Now, whilst I say you don't need to learn anything, whilst I say you have to learn this, ultimately, if you just remember these 4 steps, that will get you across the line. And here's the only problem though, right? We've done all this work, but we don't know what the inverse of A is. So now we have to work out what the inverse of A is. What is the inverse of A? Well, to find the inverse of A, the very first thing we need to do is we need to find the determinant of A. Can someone calculate for me what's the determinant of A? Or tell me. And how did you calculate that?
5 times 3 minus 7 times 2.
5 times 3 minus what? 5 times 2 minus what?
14.
Yeah, minus 14, which is 2 times 7. So that's going to give you sweet. So that means the inverse of A is going to be 1 over 1 because that's the determinant. Determinant is 1. Multiplied by, we swap the two corners, 3 and 5 get swapped. And then we put negatives at the front of the other two. -2, -7. Great. Cool. Now we have the inverse of A. So what we can do is we can put that here. X equals 3, -2, -7, 5, all multiplied by 21, 29. Where the heck did that come from? Well, remember, we've already done B. Right? We've already said B is there. That's what B is. We said that at the start. There's B. All we do now is we just put the inverse of A. Now, if I was to multiply these along, this is going to be painful, by the way. Just sorry. So I'm just going to let you know that this is going to be painful. I would get a 2 by 1 matrix. I'm going to end up with 3 times 21 minus 2 times 29. Now, normally that would be a plus, but because it's a negative, that becomes a negative there, a minus. And the other one is going to be, the other one is going to give us, let's go for red, -7 times 21, and then -7 times 21, and then that's going to give us 5 times 29 plus 5 times 29. Three times 21 is going to be 63. 2 times 29 is going to give us 58. 7 times 21, 147. 5 times 29, 145. Which gives us our final answers. Oh. -63 minus 58. Which is 5. -47 plus 45. 145 is equals -2. And that is the same as x. And x is equal to x over y. So that means x equals 5, y equals -2. And that, ladies and gents, is how you multiply, how you solve simultaneous equations. Now, for all of you people that walked into general maths thinking, hey, general maths is easy. General maths is the easy maths. I don't have to work hard at general maths. This is one of the reasons why I'm like, hey, sometimes general maths can be as complex as methods. I would actually say this is equivalent to a methods subject. This is equivalent to a methods exercise. So yeah, let's go. That is a lot of work, someone said. It's like, yeah, dang, it is a lot of work to solve one of these things, because you need to do more than just, hey, you need to bring all of the ideas together that we've learned. You need to have matrix multiplication, and you need to have invert. You have enough idea of what the identity is, and you have to find what an inverse is. no, you cannot just use elimination method. Whilst that is great, and yes, you could use elimination method here, the purpose of this is to show you the power of matrices, not to show you, not to get you guys to just use the method. But it does open up this idea that, hey, why do we have these complicated, why do we make these, you know, as I always ask you guys, it's like, there must be a reason for doing it. Otherwise we wouldn't do it. Like, what is the purpose of it? So yes, there is a reason for it. The reason that we need to learn about matrix solving of problems is because it's part of, it helps us when we have multiple equations. Yeah, you don't have to use this method on the exam unless they say solve this using matrix multiplication. Solve these simultaneous equations using matrix. But what you might get is you might get like half of this and asked to be like in a multiple choice question and be like, what would they be the next step? So that's one of the reasons why. A lot of people go, oh, will I be asked to do this? It's like from start to finish? Maybe, maybe not. Would you be able to ask to do part of it? Could you be asked to be like, what would be the next step? How do I convert these two equations into a matrix for matrix solving? Then yeah, you could legitimately be asked that. Someone then asked, will we get these questions a lot in test exams? Well, Dylan, my answer to that would be this. How many marks do you think a question like this would be worth? How many marks do you guys think this would be worth? 4 or 5? So I would probably say, let's see, if I had to do this, I'd say, if I had to guess, I'd say this would be, whoa. If I had to guess, I'd say this would be worth 1 mark, converting into, this would be worth 1 mark. This would be worth, would finding the determinant, this would probably be worth, would that be worth 1 or 2? It's probably worth maybe 2. And then this here, the matrix multiplication is probably worth 2. So yeah, you're looking at about a 6-mark question. And my question for you would be like, will this show up much on tests? My answer to you would be, how many times have you seen a 6-mark question on a test? And if you have, how many 6-mark questions do you see on tests? Hopefully that gives you an idea is, if you're making a test, would you want to ask a question like this? Or would you rather ask 6 smaller questions instead? So I do legal studies, so every question is a 4 or 6 marks to me. Okay, so fine. The answer is there's not going to be many of these on the test. If anything, there'll be 1 if you're unlucky, but you know, but it's unlikely that very unlikely that you'll get more than 1. Now here's the question: would you guys like me to do another example, or would you guys like to start working on 5J? That's your options here, ladies and gents. Or you can work on the revision sheet. So I handed the revision, both the revision sheets to the exam and the revision sheet to the other thing. Okay, so some of you guys want to, Elna wants to start. Is anyone else with her? Does anyone agree? I don't want to do another example. I just want to try this out for myself. Yeah, okay. So